Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo, studying chemical physics. Today I'm going to be helping you through some high school level and college level calculus problems. Be sure to check out the links in the description if you're in need of any extra homework help or would like one-on-one tutoring. Okay, let's get into it. So for our first question, we would like to prove that d over dx of secant x is going to be equal to secant x by tan x. In order to do this, we're going to need to recall the fact that secant x is equal to 1 over cos x. And because of this, we can use the quotient rule. And the quotient rule simply states that the derivative of f of x over g of x is going to be equal to g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. So if we set f of x is equal to 1, f prime of x will thus be equal to 0. If g of x is equal to cos of x, then g prime of x is equal to negative sine x. This is the derivative of f of x and of g of x. So that means that d over dx of 1 over cos x is going to be equal to g of x, so cos x multiplied by the derivative of f of x, that's going to be 0, minus f of x, which is 1, multiplied by the derivative of g of x, which is cos of x, and that is going to give us negative sine x, all over g of x, so cos x squared. Let's rewrite that. This is simply 0, and that is going to give us negative times negative, which is positive, sine x over cos squared x. We can again rewrite this as 1 over cos x times sine x over cos x. Remember that this is secant of x, and this is tan of x. This means that, finally, the derivative of secant x is equal to secant x multiplied by tan x, and that is going to be our final answer. Okay, on to our next question. We would like to solve the differential equation and find the exact answer, so not including c. If we have df over ds is equal to 12s cubed, and we have initial value problem of f of 1 is equal to negative 2, and now we want to find f of s. So first we're going to move this ds over here by multiplying both sides by ds. So these cancel, and we get d of f is equal to 12s cubed ds. Next we integrate both sides, and we get f of s is equal to 12 we're just going to bring this 12 right on out because it's a constant, times the integral of s cubed ds. And you need to remember that the integral of x to the a is equal to 1 over a plus 1 x a. You can prove this by simply, a plus 1. By simply taking the derivative, and we'll bring this down so that they cancel, and subtract 1, leaving a. Let's just rewrite that. Which means that the integral of s cubed is going to be 1 over a is equal to 3, so 3 plus 1 is going to be 4, x 4. So x to the power 4 over 4. If you take the derivative, 4's will cancel, leaving x cubed. Sorry, our variable is s here. Not x. Okay, so let's just rewrite that. And remember, since there are no bounds, it's going to leave a plus c. Now, since we have an initial value problem, let's simplify this first, leaving 3. So we know that the general solution is going to be 3s to the power 4 plus c. But we want an exact solution, and we're going to use the initial value problem. So we know f of 1 is equal to 3 by 1 plus c, and that is going to give us -2. This means that 3 plus c is equal to -2. Bring this right on over here, and we get c is equal to -5. So once we put that right back into our general solution, the exact solution for this initial value problem is going to be f of s is equal to 3s to the power 4 minus 5, because that is our c value in this case. And that's going to be the final answer. Okay, next up, we would like to find the area of the shaded region. And there are going to be 2 ways in order for us to do this. So we have 2 methods. We have the calculus 1 method. That is a simplification / is derived from the more straightforward calculus 3 method. Okay, so first, for our calculus 1 method, we know that the area can be determined by integrating from a to b the upper function minus the lower function over dx if x is bounded by a and b. So a good way to visualize this case is case A, where you do have your upper function. So this is going to be y is equal to the cube root of x. Your lower function, which is going to be y is equal to x to the -1, so 1 over x. And the functions are bounded by x is equal to 1 and x is equal to 27. The second way is by taking the integral from a to b of the right function minus the left function. Over dy if, let's use different variables for our bounds. So between c and d, if y is bounded by c and d. So a great way to visualize this would be our second case, where we have our right function. So the function to the right is e to the y. So right here. The function to the left is going to be x is equal to y squared minus 3. And lastly, our bounds are y's between -1 and 1. Next up, we have the calculus 3 method, which generalizes both of them into one clean calculation. And this would just be a is equal to the double integral over region D, which is what's shaded, over D, A. And dA, if we're in Cartesian coordinates, is going to be dx, dy. And so now let's use them so that you have a better understanding of what we mean. And so for A, let's start with the calculus 1 method. So the first method, which is using the upper function and the lower function, we know that our bounds are going to be x is between 1 and 27. Our upper function is going to be the cube root of x, and our lower function is going to be 1 over x is equal to y is equal to y. And so let's just write that out, and we get a is equal to the integral from 1 to 27 of the upper function, so the cube root of x minus the lower function all over dx. Let's rewrite this in, let's break this up actually using properties of integral. So we know the integral of a minus b is equal to the integral of a minus the integral of b. So let's rewrite it. And additionally, we want to rewrite the cube root of x as x to the power of 3 over 2. So it becomes the integral from 1 to 27 of x to the power of 3 over 2 minus, over dx minus the integral let's not break it up. Let's just rewrite it in a form that's more understandable. So 1 to 27, x to the power of 3 over 2 minus x to the power of -1 dx. And so we need to remember that the integral of 1 over x is equal to ln x, and the integral of x to the power of a is equal to 1 over a plus 1 x to the a plus 1. So for x to the power of 3 over 2, the integral is going to be 1 over 3 over 2 plus 1. 3 over 2 plus 1 is going to give us 5 over 2. And then the inverse of that is going to be 2 over 5. Sorry, this is supposed to be 1 over 3. Not 3 over 2. So this becomes x to the power of 4 over 3 by 3 over 4 minus ln x. And since it is a bounded integral, we want to take it from 1 to 27. This will become 3 over 4, 27 to the power of 4 over 3 minus ln 27 minus 3 over 4, 1 to the power 4 over 3 plus ln 1. And this final answer becomes 60 minus ln 27. Now, using the second method, we need to define D first. So we'll be using Cartesian coordinates such that x lies between 1 and 27, as we defined earlier, and y lies between 1 over x, cube root of x. And now we simply take the integral over that. So a would be equal to the integral as x goes from 1 to 27, the integral as y goes from 1 over x to the cube root of x, of dx, let's take y first, dy dx. So first we're going to deal with this part, and this just becomes 1 to 27 of y, 1 over x, cube root of x, dx, and this becomes what we had seen previously in the calculation, 1 to 27 of cube root of x minus 1 over x dx. And then the calculation will continue just as it did if we use the calculus 1 method to give us the same answer of 60 minus ln 27. So we can see that the calculus 1 method comes from here. We just decided to describe this part with our words and jump straight into this calculation. Next up, we're going to be doing part B using both. So start with calculus 1 method of B. We're going to be using the left and right one. And so we know that y is bounded by -1 and 1. And x is bounded by y squared minus 3. E to the power of y. So this means that we will be taking a will be equal to the integral from -1 to 1 of the right function, so e to the y, minus the left function, so y squared minus 3 dy. And this will be the integral from -1 to 1 of e to the y minus y squared plus 3 dy. Now this is going to give us, remember the exponent rule here, simply e to the y minus 1 over 3 y cubed plus 3y from -1 to 1 since it's bounded. And that is simply going to give us e minus 1 over 3 plus 3 minus e to the -1, so that's going to be 1 over e plus 1 over 3 minus 3. And this will give us our final answer of 16 over 3 plus e plus 1 over e. And that's going to be our final answer. If we use the calculus 3 method, again, we should get the same exact thing. So we, of course, first need to define D. We're in Cartesian. And x is going to be bounded now by this, and y is bounded by this. So the area is going to be, let's put the y1 on the outside because it's easier. So -1 to 1. Y squared minus 3 to e to the y dx dy. If we do this part, we're going to get exactly what we got as the first calculation for the calculus 1 method, and that's going to be -1 to 1. We get x, y squared minus 3 dy, and this is going to get -1 to 1 of e y minus y squared plus 3, which is exactly what we got last time, dy. Calculation proceeds exactly as it did if we use the calculus 1 method, and we finally get 16 over 3 plus e plus 1 over e. And that's going to be our final answer. Okay, for our next question, we want to find the power series representation for this function. So if we have f of x is equal to inverse tangent of x squared. So first we're going to need to find the power series representation for the inverse of tan. And so we know that the derivative of tan x is equal to 1 over 1 plus x squared. So we can just rewrite this as the inverse tan is equal to the integral of 1 over 1 plus x squared. And now we need to remember the cheat sheet, if you'd like to call it that, of 1 over 1 minus x is equal to the power series from n is equal to 0 to infinity of x to the power of n. So in the scenario where we have 1 over 1 plus x squared, let's rewrite it on this side. That is the same thing as 1 minus negative x squared. So let's just put that in. And let's rewrite this in a simpler form. To the power of 2n. So if you want to get the power series representation of the inverse of tan, we'd like to take the integral of what we have just written out because the two are equivalent. So -1 to the power of n x to the 2n. Let me just ensure everything is okay. Okay, and so we need to, these don't have any dependence on x, so technically you can pull them out, but it won't have any effect. And so we just need to remember that the integral of x to the a is equal to 1 over a plus 1, x to the a plus 1. So this means that this is going to be equal to the sum from n is equal to 0 to infinity. -1 to the power of n remains unchanged. A is going to be 2n. So a plus 1 is 2n plus 1. So x to the 2n plus 1 over 2n plus 1. So that's going to be the first step. Next, if we want the inverse tan of x squared, we're going to have to replace this x with x squared. So that becomes 4n plus 2. And we know that all of this all holds in the condition that the absolute value of x is less than 1. So let's rewrite that. And finally we get x, we're going to multiply this. So that becomes 4n plus 2 over 2n plus 1. So that's going to be our first answer. So the power series representation is 10 to the negative x squared is equal to a summation from n is equal to 0 to infinity of -1 n x to the 4n plus 2 all over 2n plus 1. Next, we will want to find the interval of convergence, and we're going to do this with the ratio test. And you just need to remember that the summation converges as long as L is less than 1. And we need to recall that L is equal to un plus 1 over un if un is this. So L is going to be equal to -1 n plus 1 x to the 4n plus 6 all over 2n plus 2 plus 1 multiplied by, this is going to be the un part, so -1 n x to the 4n plus 2 all over 2n plus 1. And this is going to give us -1. Oh, sorry, it's supposed to be the inverse. To write that, because it's the denominator here. So n plus 1 minus n x to the 4n plus 6 minus 4n minus 2 all multiplied by 2n plus 1 over 2n plus 3. This just becomes -1, and this becomes 6 minus 2, so x to the power of 4, and the magnitude of -x to the power of 4 is just x to the power of 4. So, sorry, magnitude of x to the power of 4. So, sorry, L is equal to the limit as n approaches infinity of this. And so we can just pull out the x to the power of 4, and it just becomes x to the power of 4 times the limit as n approaches infinity of 2n plus 1 over 2n plus 3, which of course cancels to become 1. So this finally means that L is equal to the magnitude of x to the power of 4, and we want this to remain less than 1. And this is the same thing as, remember that x to the power 4 is equal to x squared by x squared. And then we can make them individual. So it's the same exact thing as x to the power 4. So this means that the magnitude of x to the power 4 is less than 1, which means that the magnitude of x must be less than 1. So this simply means that the interval of convergence is going to be when x is between -1 and 1. And that's our final answer. Okay, on to the next question. Use your calculator to find the coordinates of any relative extrema, and the function f of x is equal to x cubed minus x. And then use your calculator to graph the derivative of that function, find the zeros, and what connection is there between the extrema of f of x and the zeros of the derivative of the function. What rule has been illustrated by this? So let's first find the extrema of f of x. So we find the extrema by, so if f of x is equal to x cubed minus x, we find the extrema by taking the derivative first and setting it equal to 0. So this becomes 3x squared minus 1. And we like to set it to 0 and then test points before and after it, because when the derivative of whatever function is 0, that means we are at a maximum point. So we want to find out what the derivative would have looked like before. So if it's positive, it would be pointing that way. If it's negative, it'll be pointing this way, for example. So you'd get, for points less than 0, you should get the derivative is greater than 0, so it's positive. And for points above 0, you're going to get a negative if it was this function. So let's test out what our function is going to look like. So first, let's find those points. So we have 3x squared is equal to 1, which means x squared is equal to 1 over 3. And this leads to the conclusion x is equal to 1 over the positive and negative square root of 3. So let's test values before and after that. So, we have 2 points. 1 over square root 3, and -1 over square root 3. So to test points before this one, let's choose -2. Between these two, let's choose 0, and above this, let's choose 2. So testing -2, we get 3 by -2 squared minus 1. That's going to give us 12 minus 1, which is 11. So before our point 0, we're going to expect a positive. Next up, we check 0, and we get 3 by 0 squared minus 1, and that's just going to give us -1. So you expect a negative gradient. And then next up, we're going to test 2. So 2 squared minus 1, that's again going to give us 12 minus 1, which is 11. So you expect another positive. So our function should look something along the lines of this. And we should be expecting this to be, this point where you have a turning to be -1 over square root 3, and the second point where you have another turning to be 1 over square root 3. So here we have positive, just as we expected, negative in between them, positive before. So this sketch is generally correct. Next up, let's find the zeros of this function. So we're going to need to find the derivative of that function. And that's just going to be equal to 6x, set it to equal to 0, and that's going to be at x is equal to 0. And so if we test points before and after, sorry, this is our turning point. It's going to be our extrema. Our zeros are at 3x squared minus 1 is equal to 0. And so again, we are going to get negative 1 over square root 3 and 1 over square root 3, which is the exact same points where we had the extrema here. So what this demonstrates is that the zeros of the derivative of the function are going to be the extrema of the function itself. And what this is demonstrating is the relation between zeros and relative extrema, but in functions that are derivatives of one another. And if we just quickly plot the two on Desmos, you'll see it a bit more clear. And so you can see that the turning point here, sorry, the 0 here is the turning point, and the 0 here is again the turning point. And that's it for this question. Okay, next up, we will be finding the curl and divergence of the vector field given f. So we're just going to rewrite it into, so we're given the vector field is xi plus yj plus z, okay? And this is the same thing as if you write it in vector form, x, y, z. And so for the divergence, we want to take the dot product between these two. And you need to recall that this is simply equal to d over dx, d over dy, d over dz. So the dot product between the two is just to write it all out. And this is going to give us the derivative of x with respect to x, plus the derivative of y with respect to y, plus the derivative of z with respect to z. And this is going to be 1 plus 1 plus 1, giving us 3. Next up, we want to calculate its curl. So again, just remember that that is equal to z and f is equal to x, y, z. So the curl is the cross product between the two, and that is going to be the magnitude of this and this is simply going to give us, let's write it down at the bottom here. So for our x coordinate, we're going to have the derivative of z with respect to y minus the derivative of y with respect to z, comma, for the j component, it's the negative, so it's going to be the derivative of x with respect to z minus the derivative of z with respect to x. And lastly, for the k component, we're going to have the derivative of y with respect to x minus the derivative of x with respect to y. Now, clearly, this is going to be 0 minus 0, 0 minus 0, and 0 minus 0, all giving us the 0 vector. And that's going to be our final answer. Okay, for our next question, we would like to convert from polar coordinates to Cartesian coordinates an equation. So we have r secant theta is equal to 3. And you need to remember how to do these conversions. So remember that x is equal to r cos theta, y is equal to r sine theta, and sorry, we are in polar, and r is equal to the root of x squared plus y squared in order to get us into polar coordinates. And so if we want to rewrite this equation, let's first remember that secant theta is equal to 1 over cos theta. So rewrite that as r by 1 over cos theta is equal to 3. Multiply both sides by cos theta to cancel, and we get r is equal to 3 cos theta. And lastly, we want to change this into r squared, so multiply both sides by r. So we can get r squared is equal to 3r cos theta. Now you need to remember the fact that x is r cos theta, and r squared is x squared plus y squared. So this becomes x squared plus y squared is equal to 3x. So now we want to rewrite this equation, and we get x squared minus 3x plus y squared is equal to 0. So, and remember that if we have x plus a squared, we get x squared plus 2ax plus a squared. So let's rewrite this in this form. And so you have 2a is equal to negative 3, a is equal to negative 3 over 2, a squared is equal to 9 over 4. So x squared minus 3x is the same thing as x minus 3 over 2 squared minus 9 over 4, because we want to take out that 9 over 4 that would be left over here. So just write that all out, and we get x minus 3 over 2 plus y squared minus 9 over 4, and just bring over that 9 over 4, and our final form becomes x minus 3 over 2 squared plus y squared is equal to 9 over 4. So this would be describing some form of a circle with this and this as your radius. If you just remember the general equation, x squared plus y squared is equal to r squared. That's it. So for our next question, you want to find the integral of cos squared x and we're just going to use a double angle formula to express this in a way that is easier to integrate. And the double angle formula is cos 2x is equal to 2 cos squared x minus 1, which means that cos squared x is going to be cos 2x plus 1 over 2. So let's just rewrite that over here. So this is equal to the integral of cos 2x plus 1 over 2 dx. So let's just pull out the 1 over 2. And then we can rewrite this as 1 over 2 multiplied by the integral of cos 2x dx plus the integral of 1 dx. And then we're going to use substitution in order to figure out what this is. So if u is equal to 2x, then du over dx is equal to 2. So dx is equal to du over 2. So this becomes a half multiplied by the integral. We're going to pull out the over 2. So again, 1 over 2 cos u du, once you substitute that all back in here. And the integral of 1 dx is just x. So we know how to find this, and this is going to give us negative, it's going to give us sine u. And then you want to put back in that 2x, so sine 2x. So this becomes, and then it was multiplied by 1 over 2, so over 2 over 2. So this just becomes a half multiplied by sine 2x over 2 plus x, leaving us with sine 2x over 4 plus x over 2. And then let's not forget about the plus c, because we didn't have integration bounds. And that's going to be the final answer. Okay, next up, we want to find the general solution of the differential equation given to us. X to the power of 3 over 2. So again, we're just going to move this dx over here. So multiply both sides by dx. Cancels. So dy is equal to x 3 over 2 dx. And then you're going to want to integrate both sides, and this becomes y is equal to, recall that the integral of x to the power of a is 1 over a plus 1, x to the a plus 1. So in this case, a plus 1 is equal to 5 over 2, so 1 over a plus 1 is equal to 2 over 5. So it becomes 2 over 5 x to the power of 5 over 2. Plus c, because it did not have any integration bounds, and that becomes our final answer. And for our last question, you want to find the integral of e to the u over 1 minus e to the u squared du. So for this, we're going to be using some substitution, but instead we're going to use x as the variable because we already have u. And you're just going to write x is equal to 1 minus e to the u, which means that dx over du is equal to negative e to the u. So du is equal to dx over negative e to the u, and we can just, leave it like that. And so when you put that all in, the e to the u's cancel, leaving a negative, and you just get 1 over x squared. So let's write that out. 1 over x squared dx. And this is just negative. Let's leave the negative in actually. The integral of negative x to the negative 2 dx. And again, remember the integral of x to the a is simply equal to 1 over a plus 1 over x to the power of a plus 1. So in this case, a is negative 2, so a plus 1 is going to be negative 1. So it becomes negative x to the negative 1 over negative 1. These two cancel, just leaving x to the negative 1, which is simply 1 over x, and then we simply back substitute 1 over 1 minus e to the power of u. And that's going to be our final answer. Oh, plus c, because of no integration bounds. Don't forget about the plus c. And that is all of the questions that I have for you today. I hope you enjoyed today's Q&A. If you would like to be notified, be sure to hit the subscribe button and the bell next to it. If you'd like to submit your own questions, be sure to check out the link in the descriptions. Remember to like, share, and comment if you can. This has been Marlyn from OneClass, and hope to see you next time.